You made it! Cool, right? You may be wondering how this all works. Well, there are three important words when thinking about watermarking. These are visibility, detectability, and robustness. Visibility is a watermark's ability to be perceived by the human eye. We obviously want this to be as low as possible. If people can see the watermarks on top of the images, we might as well be using QR codes. And what is this, 2006? Detectability is the watermark's ability to be detected by a computer. We want this to be as high as possible. If a watermark doesn't have a high enough detectability, it's just a regular old picture. And what is this, the 5th century BCE? Robustness is the watermark's ability to maintain its detectability even after being transformed. Going through any kind of size manipulation and image processing will stop a watermark from being detected. Similarly, obscuring it may have the same effect. We won't talk too much about robustness in this video, but a good balance between visibility and detectability are two very important things to a useful watermarked image. We can set a ratio between these two values using a variable watermark strength. But I know what you're thinking. Enough vocabulary, let me tell you how this sorcery works. Well, as you probably know, each pixel has a color value associated with it. In the RGB color space, for example, a pixel's amount of red, green, and blue determines what color it is. In digital watermarking, we increase or decrease these values by factors of the image's watermark strength to encode the image. The watermarking engine uses an interesting phenomenon known as luma variance to achieve imperceptibility. Humans see green much more easily than they see red or blue, so the watermarking engine shifts green by the amount opposite to what they set blue and red. For example, let's say you want to shift a pixel by 3. We can use these rules to determine what each color shift is going to be. So blue shift is twice the opposite of green shift. Green shift is 80% of red shift. Red and blue are the opposite of green. So if green shift is for a pixel shift of 3, red shifts by 3, which makes the green negative 2.4 and blue 4.8. Decimals are okay for this because they average shift for a number of pixels. So for 4.8, some will be shifted by 4, but most will be shifted for 5 for an average of 4.8. So how does the computer read these changes? If you take a look at the Fourier transform into a 2D frequency domain, you can see that these changes are actually quite easily detectable. Let's talk about how Watermark Assist sets the viewing distance. We know that there is a correlation between the viewing distance, which is again how far away your device is, and your watermark resolution, or the number of watermark elements per inch. A watermark element is just one bit of data. We find this correlation by testing data points and analyzing them through regression and modeling. This means that we can set a viewing distance by watermarking an image at a specific watermark resolution. It should be stated that the viewing distance is technically a geometric mean of the minimum viewing distance and the maximum viewing distance. We can test for the detectable range, and the geometric mean is the point where you're most likely to be easily able to detect. This is why you don't have to have the watermark some exact distance away from the device to be read. There's a range. So those are the basics of watermark technology. Keep following the packet for more information, or try your hand at creating a watermark at the Watermark Creation Station.